want to share with you the GitHub repository that we will going to work on. And please, if anyone find the Zoom link, share it via our Facebook group and other media. So if someone want to get and catch up with us. Now, this is the GitHub link. I want it to be under your hand while we are presenting. Let me just start the presentation. Okay, so our presentation, our workshop is about the transformer network. Firstly, what is transformer network? Transformer network is a novel neural network architect that's been proposed in a paper called Attention is All You Need. This paper by Google in 2017. And its main goal that we replacing the recurrent neural network and the convolutional neural network in the encoder decoder architect. Of course, many of you, if you have working in machine translation, the most used way is to use encoder decoder architect, where you're using the encoder to encode the incoming, let's say the source language is Arabic, and this encoder will make a mid representation for this input, and then we'll give it to the decoder, where we're using the decoder to give us the output for the next or the target, which is maybe English or French. Now this network has outperformed all the previous work in this field, and the most important part it is that it is highly efficient, and it's very speed, and it's because you will see in the next slide it's outperforming especially the recurrent neural network in the main bottlenecks for this network. But firstly, this network is solely based on what we call attention mechanism. And we want first to understand what is attention mechanism, then we will move to the transformer network. Before understanding the attention in the neural network, we can define the attention in physiology. So the short definition is that the ability to actively process specific information in the environment while turning out other details, non-important details. For example, that when you're looking at a movie in the TV, when you want to read the translation, you are going to ignore the most part that your eye is seeing and focusing on the part of the translation. So also there is this definition by William James in the Principle of Physiology, which referring to the same definition by implying withdrawal from some things in order to deal efficiently with others. So we're focusing on most important part. That is the main idea or the concept of attention. Looking back to the attention, it's been proposed in 2014 by the paper called Neural Machine Translation by Jointly Learning to Align and Translate. I want you to look at this part, this image. If you're looking at the zone, which is in French, and you look that the model giving high focus or high attention weight or score to economic and area, which is the related to this word in real. Now, what is defined that by this paper that it's by the attention is to allow the model to automatically soft searching in the source sentence to where we focusing on the relevant to the prediction or the target word. More example about attention in the image captioning. So this is from paper in 2016. If you're looking at this image that this is the source image. This is the source image when we want to create a caption for it. Now, when the model generate the word giraffe, if you look here, the white is the attention weight or the score, or where the model look when it's generating the word giraffe. Now, if you focus that the model is actually looking only on this place of giraffe when it's generating this word. if you're looking down here to the zebras, now the model ignore every part of the image and giving high probability or high score or weight, attention weight to the zebra location in the source image, and so on the other section from this paper. Now getting back the transformer network main characteristic, why we need it, what its came, what its advantages. The first thing is that transformer network is not a sequential. So if you work in natural language processing, or you have implementing any kind of RNN and its variant like LSTM, GRUs, that this kind of network is a sequential, and this is a big bottleneck for it. So it's bottleneck because we want to benefit from the modern hardware and the parallelism. We cannot benefit from it when you're using this kind of network, because when we want to feed this sentence, how are you? We wanted to feed it by time step. So firstly, we're feeding x time t, which is how, then x t plus 1, which is r, and xt plus 2, which is u. While in a transformer network, we feed the whole sentence at once, and this will give us the parallelism and will benefit from the parallel processing. The second characteristic is that the use of self-attention. Now, when the attention mechanism has came, there is a modification has been applied to the encoder decoder part by making, by adding attention to LSTM or the convolution, and it's give good advantages. But in this in this transformer network, the attention is being taken from the input itself. This is what called self-attention. So we got the input itself, and we take 3 copy from this input. One, we call it a query, and the other is the key, and the other is the value. We calculating the attention, and we'll see how it's being calculated both in code and formula. But let's just see that this is the whole process of taking self-attention from the input. Now, what is the benefit from the self-attention? Let's see this example. Now, firstly, that in French, animal and street have different genders. So when you translate it, it's had different translation. Now, let's look at the first sentence. The animal did not cross the street because it was too tired. Now, this it is referring to the animal, not to something else in the sentence. While the second sentence, the animal did not cross the street because it was too wide. Now, this too wide is referring to the street. For the old way, this both sentence, the model cannot differentiate between them. But by using self-attention transformer network, if you're looking at this image, it here, this is the score or the attention weight. That's the model giving the highest attention or attend to the word animal. So it's making relation between it and animal, which is the proper way to translate this if you give it to human. Now in the second sentence, because we're using the self-attention, when taking the attention from the input itself, the model looked at that this it referring to the street and not to the animal, and it's giving the highest attention weight to the street. So this is why the model was able to present 2 different translation and correct translation when we give a fully similar sentence, but changing just this wide and tired, which for us as a human, we knew it, but in the old ways, the model cannot attend to it. Now, using self-attention help us to do this. The another part is that it is not just a self-attention, it is a multi-head self-attention. What we mean by this, that the model is not just looking or attending to different word of the sentence, but it's also taking attention to different segments in the sentence. So because the model, when it's learning, will divide the embedding by the number of heads. So it will take different segments from the sentence and try to calculate its context vector or its attention weight that related to the given word. So now for it, the model have different segment. Each segment represent a context vector, have its own self-attention, and this will help the model to attend to specific part in the sentence. Now let's study the transformer network. This is the main architecture for the transformer network. If you're not looking at the details, you know this is the encoder part, and this is the decoder part. Now, this encoder part, what it does in any machine learning, so if we taking transformer or something else, that we give an input when we taking out a mid-level representation that's been learned by this encoder. This mid-representation can be used in the decoder to give us the output, desired output, whether it is word generating, translation, and something like this. Now, this is the main design for encoder decoder, but the change is in the part of these. For transformer, if you look in, there is a simple pre-processing plan, which is me. If you study, when we will study it next, you will see most of this something that you know it, but it's not something new. But what is new is the multi-head attention and the masked multi-head attention. This is what's came. This is what's new inside the transformer. Other part you already has been see it or learn it or see it in somewhere else. Now there is this block, which is the residual learning. We will move next to it and understand it. So firstly, we start by inputs and moving on to the next part. So the first thing that we do is input embedding. Now, what we're doing by input embedding, we're taking some kind of representation to the input. We firstly try, as we said, that this is non-sequential. It is taking the whole sentence. So what we need is that we want to calculate the maximum length of the sentence we want to feed it to the model. So let's say we have the full sentence or the maximum length for our sentence in this example is the 10 words. Now, any sentence has less than this length, we can pad it with the zeros. So if there is a sentence with a 5 word, we can add 5 zeros in the end of it. Now, if there is came a sentence more its length bigger, we can truncate it. So restricting with this example, the first thing that we do is that we want to take some input sentences and do word embedding for it. And we want the shape to be batch size, and the maximum length we said here is 10, and the dimensionality of the word embedding. You already maybe studying some kind of word embedding like word2vec and some kind of tokenizer that inside many models. Now next, because in this part we catching the meaning of the word or the representation of the word itself, we want to catch the position information, because we said that the model accept the full sentence at once, but we know that we need to understand the position relation for the words. So we doing this, there is many kind of position encoding. There is a learnable way, and there is this way where we generating sine and cosine waves. So this is the equation, if you're looking at it, that we generating a sine wave for each even number, and we generating a cosine wave for each odd number. What I mean by odd and even, that if we said that we have an input with the shape with the word embedding shape of 512, so we want to generate 512 waves. Each wave came from equation for it. Even it's even, so we will generate sine, or if it's odd, we'll generate a cosine according to this. Now, when we want to take the word number 0, we're going to project it on this waves and taking the amplitude for the word for each dimension. So let's say that the word number 0, when we want to take, we will going to add the amplitude of dimension 5, which is here 1, to the whatever the value in the embedding, in the word embedding that's been represented from the input embedding from the previous stage. Now with this, we capturing the position information, and with this, we are ending with our pre-processing stages. Next, we let's see this embedding and positional encoding in the code. I want you to open the GitHub that I give it to you, and you open this transformer.py. So we're going to study this class. Okay. I like to, when we are working here from PyTorch, so I want to describe it from the entry point. So the entry point is the forward in this classes in PyTorch. What we are doing, the first step is embedding. We're calling this embed and inputting the word. Now this is just for normalization. The embedding, actually, we are doing this nn.embedding, which actually creating a lookup table. This is some kind of tokenization. You can just searching for it. Now we create it with a size of vocabulary size and the dimensionality of the model. Next, we are doing summation between what we got from the positional encoding and the embedding. So how are we calculating the positional encoding? This is the method that we calculated. So as you see, firstly, I created a zeros matrix with a maximum length and dimensionality that, as previously we said. Now we just making a loop over the positions. We taking 2 steps each time. We creating a sine wave for each even number and creating a cosine wave for each odd number of the dimensionality. Now here just we are unsequencing. What I mean by unsequencing that, because we are going to add batch size maximum length dimensionality, which is this, the embedding. When we add it, we need this to be the same shape. There is a place for batch. So we unsequencing, we adding a dimensionality of 1 here and keeping the other dimensionality. So the addition will be, so this will be broadcasted to its correct position, and we are going to complete the addition. Now, this is just the step of pre-processing or the embedding, both the word embedding and the positional encoding. So we want to get back to our presentation. We're moving on forward. This code, we are just going to see it in a pure implementation, not using any library. Then when we move to the concept of BERT and vision transformer, we are going to implement it in real world data. So we are just seeing how it's implemented in a pure code. Now, we have described it. The next part is that we calculating the multi-head attention. So let's firstly understand the concept. Now we talk about there is a self-attention. The multi-head self-attention, the multi-head attention is just a stack of a self-attention. We are just going to do multiple self-attention. But what we are going to do, firstly, as we said, that the first thing that is the input, we are going to get a 3 replica, a 3 copy from the input. So the input, if it's X, we are going to take a copy, call it value, and a copy called a key, and a copy called a query. Now, these 3 are equal in values inside it because they are 3 identical copy. So when we want to make them different in representation, we feed each one of them in different linear layer, in different neural network. So when there will be a weight, this weight is different from network to network. There will be operations that will make different outputs. So these different outputs will give us three different representation for the same input. So we will end up with the value, key, and a query. Because we have in a multi-head self-attention, we said that is a stack of a self-attention. So how it is done? We are going to divide these three values by the number of the head. So if the model said that we have 8 head, we have here, let's say that we have a dimensionality of 512. So when we divide it by 8, you are going to end up with a dimensionality of 64. So you will get 8 context vector. Each one is a dimensionality of 64. So we are going to calculate the attention operation for each the 8 context. The same operation, but for different segment, for different parts. So as mentioned here, that this is the operation. The operation, when we see it, is that just we are going to take dot product between query and the key, and taking the softmax, and then taking the dot product between the value and the output to measure the score for this part. Now, when this is done, we're going to go to some concatenation, which is just the reshaping to get back to the 512 dimensionality. And then to strengthen the representation, we are going to feed it into linear layer, a neural network. So we are going to take a strong representation for what's being calculated from this and concatenated. So let's see how the attention being calculated in a formula. The firstly, we said this is the X. We take in the query and the key. Now we already know that these are being fed into neural network, and we have different representation. So in order to do dot product, we are going to so we're taking the dot product between the query and the transpose of the key. This is just to make sure the dimensionality work together. And we normalize it by division of the square root of the decay. Decay here is that the dimensionality of each head, was we saying that 512 divided by 8, so it is representing 64. Now, when we take in the dot product, taking the softmax for it, and then taking its output multiplied by the value, and this will be as if you want to multiply this value by a weight or attention score, so it will give a higher attention to the important part from this head. Moving next, we are going to do the concatenation. Concatenation here is just a reshaping. So we said that we have 8 different context vector, each with the size of byte size, number of the head, maximum length of the word, and the decay, which is here the 512 division by 8, which is 64. So this is the real numbers. Now we are going to reshape it by byte size, maximum length, and multiplying 8 by 64 to get it back to this original shape. So we divide in it, calculating attention to each head, and then combining them by reshaping them. So to make stronger representation with it, we are going to get it into a linear layer. So this calculation will give us stronger representation because we are not going to rely just on reshaping and concatenation. So the output of this network is 512. It will accept 512 and will output 512. So we are going to take output from this as a byte size, maximum length, and 512. Moving next, let's see the code. I hope that you already opening this transformer.py from the GitHub repo that I already sent it to you via chat earlier. Now, this is the multi-head attention class. I want to study it with you. So I like to describe it from the entry points, from the forward. As you can see here, this has been inputted. So we just taking the 3 copy and give it to this forward. We are going to give the following. This query has been passed to something called self.query. What is this? Let's move on for here. That this is the linear layer or the network, simple neural networks, simple layer with a shape of dimensionality as input and dimensionality as output. The same, this is different network here for key and for value. And you can see it from here. After feed it to this network, we are going to project and reshape. So we want to make the calculation, we want to divide it, we want to do it like this way. This is the projection. So I want you to think about this, the shapes. The first thing that they input, any one of these inputs, is with this shape, batch size, maximum length, and the dimensionality of the model. We want to get this final output, but we want to open this to make it divisible by the number of the head. Because we have 8 heads, we want to calculate the decay, which is the dimensionality of the model divided by the heads. And this number must be divisible by the heads. This is something you must restrict with. So the first thing we're going to reshape by using x.view, which is normally from PyTorch. When you said x.shape 0, we're going to take this, the 0 shape, the 0 place in the shape, and we want to keep it as it's a place. So we want to keep the batch size. We don't want to play with it. And now we want, just ignore this -1, and I will describe it later. We take in the last, which is the dimensionality, and we want to break it in 2 numbers, the head and the decay. So this will be the head 8, already we know it, 8, and this is the dividable number. So this here will be the 8 context vector. Now, whatever the remaining dimension, when we give -1, the PyTorch will know to calculate whatever needed here. Next, that we're going to make a permute, because this part, until this dot, will give us batch size, maximum length, edge, and decay. But actually, we want batch size, head, maximum length, and decay. So we are permuting, we are changing the positions of these shapes. So this is the place 1 in the shape, the place 0, the place 1 here, and the place 2, and the place 3. If you look, we just want to change the position of a place 2 instead of a place 1. So doing dot permute 0, 2 instead of the 1. So this head will become here, and 1 will become here, as we mentioned it here. Now we're changing the dimensionality. We divide it and making the 8 head. We are not yet calculating any attention, but we're preparing that each input, which let's say that here we are inputting the query. After we inputting the query to linear layer and above, we changing its shape to become containing 8 context vector that we are going to calculate the attention for. Now, next, after doing this, some kind of shaping, and we are going to calculate the attention. If you look at the attention here, the first thing that we are going to take the dot product between the query and the transpose of the key. This is just we calculating the transpose, and this is just for assuring the shape of the matrix is good to take this dot product. And this is the normalization term. We are going to divide it by square root of the decay. I calculated it from taking the last shape value from the query. Now, the next thing that we said that when we padding the sentence, we are going to place a zeros in the missing place, because if we said that we have the maximum length for our ideal sentence is 10, we wanted to take, if we have a sentence with the 5 word, we were going to fill the missing word with the zeros. Now these zeros maybe become maybe the model will attend to it. We don't want the model to attend to it. So we are going to replace each zero with a very, very, very small number. So the model will not attend to these zeros and ignore it when we calculate it using just dot masked fill, which is from PyTorch. Next, we are going to take the softmax for the score that's been calculated. And this is a dropout from the paper that we want to make drop out to the weight. And then we are calculating the dot product between the value and the weight. And by this, we are taking the attention. Now, here we're reaching to the concatenation stage. So this is the concatenation method. What are we are going to do? Firstly, if you're looking at this, we are going to get back these two shapes because we want to get back to the original shape that we defined here. And in order to take it, so firstly, we are going to change this position. Then we are going to reshape. So taking the multiplication between head and the decay. So this will get back our 512. And this will, as we mentioned before, the -1 will calculate what's ever needed here to complete the shape. We are not finished yet. We want to feed it into a linear layer, which is, we define it here and initialize it here. Okay, so this is the multi-head attention, and this is how we calculate it. Getting back to our slides, I mentioned that he's just studying the code of the core transformer. Next, in the following examples, we're going to work on real data. Also, there is a form of participant in this workshop will be sent to you once we finish. Let me complete. And also, if you have any question, just put it down under your hand, and I will hear it from you, or you write it once I finish all the presentation. Let's get back. Okay. Now, the next part is the residual learning, or let me just get you back to the main block of transformer. As you can see in here that we completed this, it's just a normalization term. Now, if you look at this block, I hope that you already know the residual blocks or residual learning, because it is very core part in deep convolutional network in the computer vision. But I will give you a brief on it if you not know it. Getting back to the residual learning. So what residual learning try to learn is try to learn the identity map. It's actually learning what's remaining, and by bypassing or making a shortcut connection between the X and the f of X that's been taken from the network. This kind of work is being added to network because that they found that when we going with the traditional like FIDGE 16, 19 and others traditional convolutional neural network, when we go deeper, it's supposed that we get a better result, but what's happened is that we are going to get a worse result. And this is because some kind of a problem in going deeper without a properly architecting and the way it's being decayed, and many other parts is being studied in the paper. But the idea here is that they're adding the skip connection to let us going deeper and learning much more better representation. This residual learning is also a part of the architect of the transformer. If you want to study it, it's not a part of this workshop, but I hope that you read the paper on it if you not know it. And I suppose all of you know it. Getting back now in the decoder part, we have finished the encoder. Now the decoder part containing the same concept, except that the mask multi-head attention. So if you're thinking about the input that we said that we're giving the whole sentence at once, that in the training, it's okay. We having the model have a full viewing of data, but in inference, the model does not have the feature word. This is being proposed for, let's say that we want to do a word generating or something like this, the model has not to know the next word. It has to predict it or has to work for it. So the masked multi-head attention is just a way that we adding some kind of masking, so we prevent the model from knowing the feature word. So it's getting the current and the past only. So this is just the difference between the masked and multi-head attention.